Hello everyone, this is Group 30 and our project is titled Morse Code Challenge. Our mission is to build and maintain a project revolving a fun and engaging challenge where participants can learn and compete in writing Morse code. This system we're building will allow participants to interact with a physical button, which will then serve as an input to be decoded using Arduino and is then calculated and finally displayed on the live leaderboard rankings. This would be the artifact design of our system. It will feature an LCD screen for display, buzzer for audio feedback, and a motherboard to compute and connect the display to the Arduino. All these electronic components will be housed in a plywood housing connected to an external power supply. Most of these components will be purchased from an official electronic supplier, while the housing itself will require the team to manufacture and glue it together and put together in a suitable workshop. This is essentially how each component will communicate with one another, having Arduino and Raspberry Pi as the central brain to manage each module modularly. And most of this part is software, and therefore we'll have two main teams working together, the hardware team and the software team. On the actual day of the event, students will gather around our interactive stand and listen to one of the team members to give a quick explanation on how Morse code works in theory. Afterwards, they get to participate, allowing them to tap, allowing them to participate, where a buzzer will beep and an LED strip will flash to provide instant audible and visual feedback for every dots and dashes. The LCD screen will decode the taps in real time, and once the time is up, the student score is immediately posted to a live leaderboard, ranking them against all previous participants from that day.
Moving on to the stakeholder management plan, the analysis is firstly done by using a power interest matrix to determine each stakeholder's significance in the project and how to manage them. We both have internal stakeholders and external stakeholders. Internal stakeholders consist of the project manager, the hardware team, and the software team, while external stakeholders, they consist of the module leader or assessor, Faculty of Engineering, iForge, Octagon Center, and suppliers. So a slightly more detailed explanation for each of the quadrants in the matrix. So first one is managed closely. They have high power and high interest. They have strong influence over the project decisions. So they require continuous communication and involvement. Next is keep informed. They have low power but high interest. This group has low authority over decision-making aspects, so they require regular updates and communication. Next is keep satisfied. This group has high power but low interest. They have strong influence over the resources and deployment but low day-to-day involvement. With this group, good coordination is needed to avoid disruption or conflicts. Lastly is monitor. This group has low power and low interest. This group's engagement is mainly during procurement, and they only require minimal ongoing communication. Next is the management plan. So firstly, for manage closely, because they are highly involved in key decision making, they require weekly meetings where a detailed progress report is shared with every meeting. Next is keep informed. This group is given regular updates on the progress, where feedback from this group is collected throughout the development process. Next is keep satisfied. With this group, they only require periodic updates because making it too often might be too disruptive for this group. The updates include ensuring the requirements are met, such as the facilities and setup, and maintaining good coordination is needed to ensure project feasibility. Lastly is monitor. They require minimal communication, so only reach out to this group when needed, because unnecessary communication may cause overload. So that is the project stakeholder management plan.
So moving on to the time and cost plan, we'll be walking you through how we've planned and costed this project. In total, our project, which comes in 3,931, sits within our maximum budget of £5,000. This gives us a healthy of £1,068 of headroom, which we've factored in as contingency for anything unexpected. If you look at the bar here, you can see that the budget is dominated by labor, which makes sense because the biggest resource of this project is our team's time. Materials are actually a relatively small portion, which reflects on how we've scoped this project and for what we actually need. Breaking down further, we have 5 team members, logging a total of 198 hours across the full project at the university flat rate of £15.30 per hour, giving us a total labor cost of £3,029. We split the work across 4 phases. Design and planning will last 2 weeks, with all team members logging in 32 hours. We've decided to make hardware building phase longer at 4 weeks, but with only 2 members, so each member will be logging an extra 2 or 3 hours. In the software development phase, we'll have another 2 members working on it for 4 weeks as well, and we expect to put in 48 hours total here. Finally, integration and testing, and the event day itself will require all efforts of 5 members to bring a total labor time of the project to 198 hours.
In regards to the materials, we've sourced from either RS Components, Rapid Electronics, or the iForge in Sheffield. So the majority of the electronics, things like the Arduino, push buttons, buzzers, power supply, all come from RS Components, totaling at £360.86. The Raspberry Pi, LED strip, LCD screens, and all the cables come from Rapid Electronics at £279.05. And the housing materials, so things like plywood, acrylic sheet, and MDF, we're getting from the iForge here in the Diamond, and this comes at £81. This brings the total cost of our materials to £714.91, including VAT. On this slide, you can see our project timeline, which we've mapped onto a Gantt chart. We have 8 working weeks, from the start date of 1st of June through to the 24th of July, with the event itself happening on the 25th. So phase 1 is for designing and planning, and this covers weeks 1 and 2. Here, we'll be finalizing the system architecture, ordering all components, and getting the wiring diagrams done. This all needs to happen early, so we're not waiting on deliveries midway through. From week 2 onwards, our hardware and software development will run in parallel. So the hardware team will be over at the iForge fabricating and assembling the device, while the software team will be working on the Morse decoding logic and the leaderboard system independently. Week 6 and 7 will bring everything together. So this is where integration, debugging, and user testing happens. And week 8 is purely for rehearsal and final preparation.
So to bring it all together, £3,029 on labor, £715 on materials, and £187 contingency, giving a grand total of £3,931. We're over £1,000 under the maximum budget, which we think demonstrates that this is well scoped and has a great value for our money. The contingency is there to cover things like component failures or any small design changes, but with a schedule, this is well planned. We're confident we won't need most of it.
We have selected a wide range of tools to help us decide and make better judgment when it comes to time management. The tool we used is a critical path analysis. This table features all the activities that need to be completed by the team, with every activity given an identifier from A to J. This table features 3 possible duration outcomes, which is then calculated to form the expected duration at the far end of the table using a specific formula, which is optimistic plus most probable times 4 plus pessimistic over 6. After deciding all the activities that are dependent on each other, arranging the predecessors one by one, this is the path analysis we came up with. We then calculated the duration, earliest start time, latest start time from start all the way to finish. The project duration will take at least 34 days, with certain pathways having more room for compromises. And finally, we have identified the critical path which is AEFHJ. This path is responsible by the software team I've mentioned earlier in the presentation. For cost analysis, as presented, the labor work requires roughly around £3,000 as is. However, that is if we were to follow the expected duration. If we are to cut even more corners and use optimistic duration, then we can calculate the crash cost of the entire project. Each activity can be crashed for a few days earlier, and we have estimated each crash day to cost roughly £50, which will then allow us to reduce the project duration from 34 days to 22 days. The trade-off is an additional £1,150 extra to be spent to optimistically achieve this time. The new critical path, therefore, will be ACDGJ, which is responsible by the hardware team instead. However, since the accumulated crash cost will go over 5,000 budget we have been given, we have decided to stay with our initial plan of 34 days. This will allow more room for changes, which provides a safety net in case of emergent situation.
Here, let's discuss our risk management plan. First, let's talk about the risk identification. For the risk identification, we use 3 structure methods. First, a TCQ analysis. We review the work breakdown structure and our £714.91 materials budget through the lens of time, cost, and quality to find pressure points. Second, we looked for observable warning signs like a single supplier for all components, no confirmed integration milestone before week 5, and an untasted Arduino communication interface. Third, we challenge our key assumptions, which are full team availability, iWatch facility bookings confirmed, and all components delivered within 1 week of ordering. Next, the risk analysis. Here we use FMEA, which each risk gets 3 scores rated 1 to 5 for likelihood, severity, and detectability. Multiply the 3 together and you get a total score. We classify anything 60 or above as critical, 30 to 95 as high, 15 to 29 as medium, and below 15 as low. This keeps prioritization consistent rather than based on gut feelings. Our highest priority risk was Morse decoder timing misclassification with a score of 60. Because the user tapped Morse code differently, the software may wrongly classify dots and dashes that could frustrate GCSE students and reduce engagement. Our response is to reduce the risk by widening timing bounds and adding a guided practice tab mode. The trigger is 3 or more consecutive incorrect decodes in rehearsal, and this risk is owned by the software team. The second major risk was Arduino serial sync failure scoring 48. If communication between the Morse logic and the leaderboard fails, the full system may not work even if each subsystem works separately. Our mitigation is to define the protocol clearly. The trigger for this one is scrambled serial data in week 5 integration testing, and it is owned by both teams. High risks include hardware failure on event day scoring 30, physical stress during fabrication or repeated student use may cause a button, buzzer, or LED light strip to fail. Insufficient time for end-to-end testing, parallel development phases with unscoped integration requirements may leave insufficient time for testing scoring 24. Supplier delivery delay. Single supplier dependency may delay fabrication start scoring 80. And material costs exceed £5,000 budget cap. Unconfirmed supplier codes and stock price variation may put total spend beyond the limit scoring 24. Next, we also identify survival, medium, and low risk, such as LED screen HDMI incompatibility scoring 16, challenge too difficult for GCSE students scoring 24, team member availability scoring 12, iWatch fully booked during build window scoring 6, main power unavailable at Octagon Center scoring 5, and plywood housing dimensional inaccuracy scoring 8. Next, let's look at our risk metric. This risk metric helps us visualize these risks by likelihood and severity. With likelihood on Y, severity on X, this made it clear which risks needed immediate mitigation and which could be monitored. Here, let's look at our responsibility metric. Every risk has a response type, a contingency plan, a specific trigger, and a responsible owner. Almost everything is reduced, meaning that we lower the probability or impact. Testing time is avoided, which means we eliminate the scenario entirely by descoping early. Main power is accepted because the likelihood is low and fallback is already ready. Critically, every trigger is measurable. We're not waiting for someone to notice a problem, we're watching for specific signals. Lastly, let's talk about opportunity management. Here we have 4 types of opportunity. First, negative to positive. If Phase 3 integration finishes early, the software team gets the green light to add difficulty levels or a Morse tutorial with 0 extra cost. Second, opportunity of response. If the enclosure build goes smoothly and finishes before estimated time, we could build a third button station. Third, random good fortune. We're positioning the leaderboard to face the walkway to maximize word-of-mouth crowd attraction. And the last one is negative to positive. The whole system goes on a public GitHub with full documentation so the future students can reuse it for future outreach at no additional cost. Here are our key takeaways. Our risk management plan identifies 2 critical risks, 4 high risks, 3 medium risks, and 4 opportunities. The main priority is to reduce the technical risk early, especially Morse timing and Arduino synchronization.